Okay, so we're converging toward an answer here. 76% of us say answer number 3, which is correct. So good job. So how do we determine this? Well, again, you should draw the electric. First of all, pick a path. It's up to you. You could go clockwise or you can go counterclockwise. It doesn't matter. The relative signs will come out to be the same. You'll get the same equation. I like to go in the direction of the electric field in the wire. It just makes a little bit more sense to me. So I'm going to go that way. Okay, that's going to be the direction of my path. Okay? And in the steady state, I know that, again, the electric field is always pointing in a direction parallel to my path. So that's E1, and then that's E1, and so forth. And so I would have, well, let me just write it out. We have delta V is equal to round trip equal to 0. And so I'm going to have a delta V in wire 1 plus a delta V wire 2 plus a delta V in the second wire 1, which I'll just label that wire 1. It turns out to be the same, plus a delta V in the battery is equal to 0. Okay? So I'm going in the let's start with this first wire 1. I'm going in the direction of the electric field, and so will that give me a positive or a negative? Delta V will be negative, right? So the delta V across, basically from this point to this point, going in that direction gives me a negative. And the field is, so I would have, a negative. And we're taking an integral here, but that electric field is uniform, so it can come out of the integral. So it's really just looking at the electric field times that distance. And so we have the magnitude of E1 times that distance, which we call L1. Okay? And then I go across the thin wire, and I'm going in the direction of the electric field. So that's going to give me negative. Okay, negative magnitude of E2, and I'm getting tired of writing that magnitude signs, so I'll just write them E1 and E2. So E1 without any symbols on it just means a magnitude. E2 without any symbols on it just means a magnitude. E2, L2, okay? And then I have another length of wire 1. I'm going in the direction of the electric field, so the difference is, again, positive or negative. Negative. Same electric field magnitude as before, E1, and same length, L1. And again, they're in the same direction. Cosine of 0 gives me 1. So it's just the field times that direction. And then if I go across the battery, again, the electric field inside the battery is in that direction. So I'm going in the opposite direction of the electric field. So I should get a potential difference that is positive. And then we say this delta V across the battery is just numerically equal to what we call the EMF. Okay? And then I'm back to where I started from, so I set the thing equal to 0. And I have two terms here that are alike, so when I rewrite this, I have EMF minus 2E1L1 minus E2L2 is equal to 0. Okay? So now what do we have? We have, well, first of all, questions. Are we okay with this? Okay. Again, watch the signs. Okay, you've got to have, you could have gone the other direction, right? I could have gone in the direction of the electric field of the battery and in the opposite direction of the fields in the wire. That would have given me a negative EMF and a positive E1L1 and a positive E2L2. So all I'm just doing is multiplying both sides of the equation by a negative sign, and that doesn't change anything. The other side is 0, so that doesn't change anything. So either way doesn't matter. Okay. Can't say 1 or 2 because you have two different electric fields inside those wires. Okay. E1 is different from E2 in the second length, so it's not the same field. So you got to be careful about that.